As we have observed, in pure Aloha or Aloha alone, we saw that without incorporating any intelligence, any coordination between nodes in a network to transmit, we still were able to achieve 18% efficiency. Now, what do we want to improve to Aloha and incorporate there that helps us to achieve higher level of efficiency? For that, the next natural advancement is slotted Aloha. In this module, we shall make certain assumptions for slotted Aloha. On the basis of these assumptions, we'll look at the operation that prevents certain level of collisions and helps improve Aloha to get more advanced and give better throughput. We'll look at the performance in terms of pros and cons, and then we'd like to calculate efficiency as probability of success as we did for Aloha. These two references provide us useful insight. You're also encouraged to explore online resources. The underlying idea in slotted Aloha, which is different from pure Aloha, is that 18% throughput means 82% failure. How can we try to reduce the failures? Is by avoiding the collisions. The collisions in slotted Aloha are minimized by, number one, all the nodes are synchronized through a master clock such that each node exactly knows the beginning of a slot which is dictated by the central clock. And then each node is also forced to adopt kind of framing structure, that is, each node has to transmit within a slot, so the frame size is fixed. The underlying assumptions which determine the operation of slotted Aloha are all the frames from all the nodes in that network are of the same size. The time is specified in terms of slots. These slots are dictated or beaconed to all the nodes in the network through a centralized clock. A frame can be transmitted at max in each time slot. The nodes can only start to transmit at the beginning of the slot. It means a frame cannot be started or cannot be transmitted in the middle of a time slot. Since the nodes are synchronized, if two nodes occupy the same time slot, of course, at the beginning they start transmitting, accident is likely to happen. In fact, accident would surely happen. If that's the case, then collision is going to happen. This is what we wanted to avoid in slotted Aloha, but with the incorporation of time slot and fixed frame size, we've just been able to achieve some level of progression, not a significant improvement. The operation for slotted Aloha is when a node receives data from its upper layer, the data link layer activates the medium access control sublayer, and the slotted Aloha algorithm starts to look for the occurrence of the start of the next time slot. The moment it finds the next time slot, it immediately transmits. Now, if no one else in the network is already transmitting or attempts to transmit in the same time slot, collision would not happen, and the success is guaranteed. If a node has subsequent data to be sent, it is going to repeat the same process. If two nodes transmit in the same time, collision is going to happen. If collision happens, then this node, which we are considering as the node which started the communication as our reference, is going to look for the next opportunity. That is, since its packet has collided, it would have to wait for the occurrence of the next time slot and transmit with probability p. The factor of probability p actually determines the urgency or the desire to transmit a packet. For instance, if the value of p is 1, it means the node which just got its packet collided is going to attempt with 100% surety in the next time slot. If node has probability of transmission as 0.1 or 10%, it means there's a 90% probability or likelihood that in the next time slot the node is not going to attempt. Let's look at the performance of slotted Aloha when we have 3 active nodes which are transmitting. Let's say that these nodes colored by yellow, green, and purple transmit at will, but they follow the time slots and they have fixed sized frames. So we see here that with certain degree of randomness, these nodes have collisions, have successes, and some of the slots absolutely go empty. If you look at these 9 slots, of these 33% slots actually give success. You can easily determine, it is also even written, how many collisions took place and how many slots actually went empty, because the transmission of a frame by a node is dependent upon how urgent that node is giving importance to the transmission. Obviously, one of the greatest advantages of using slotted Aloha is that if a node gets to have an empty channel, it can occupy all the data rate which is available on that network. It is a very decentralized protocol, not 100% decentralized, because now a master clock is being generated and distributed amongst the participating nodes in the network. And slotted Aloha is not very difficult to implement, again, like Aloha. The biggest disadvantage, however, is that slotted Aloha still cannot fully get rid of the collisions. If the nodes transmit their frames and they collide, it takes a while before the nodes actually would know that their transmissions have not yielded acknowledgements. So as such, slotted Aloha does not provide mechanism to detect collision. And clock synchronization is, of course, a necessity which was not there in pure Aloha. Similar to the exercise we did for pure Aloha, if we do this for slotted Aloha, we see that we have a leverage. The leverage is, since we have slots now and a node can only occupy the beginning of the slot for transmission and the frame size cannot exceed the time slot, so what we see here is that the probability of colliding with the preceding frame and with the subsequent frame is now gone. So what we see here is that a frame in slotted Aloha would only collide if and only if there's another frame within the same slot, not a frame preceding it, not a frame following it. Because of that, as you can see with some mathematical manipulation, we can achieve up to 37% efficiency. We have literally doubled the efficiency from pure to slotted by incorporating time slots and fixed size frames.